Welcome to another video in our series called Think 6, where we discuss interesting aspects of the next generation of wireless communications, aka 6G. Today, we will be providing an introduction to the role of 5G and 6G in the Metaverse and XR experiences. What network capabilities do we need to fully unlock the potential of the Metaverse? The first answer you'll get when asking this question is that the Metaverse requires high-speed data transmission and minimal delay to provide seamless, real-time interactions. This is vital for immersive experiences and avoid issues like motion sickness in virtual environments. From the 5G application scenario perspective, where three different scenarios are defined with enhanced mobile broadband, eMBB, ultra reliable low latency communications, or URLLC, and massive machine type communications, MMTC. XR services live between eMBB and URLLC, demanding a combination of high data rates and low latency. The details, of course, depend on the targeted use case and the device form factor, its computing capabilities, and many more. Speaking about devices, the success of the Metaverse hinges on the performance of XR-based technologies and services, which are integral to creating immersive experiences. These technologies require devices that are powerful, small, light, and even fashionable, especially from a consumer Metaverse perspective. The challenge lies in reducing these devices' size and power consumption without compromising their capabilities. Efficient energy use is essential to ensure longer usage times and sustainability. This is particularly important for portable and wearable devices, integral to the Metaverse experience. Motion to render to photon latency is a critical metric in virtual reality and augmented reality systems. It refers to the time taken from the moment a user moves, motion to the time when the corresponding change is rendered and the updated image is emitted as photons from the display to the user's eyes. This latency is crucial for creating a seamless and immersive experience in VR and AR. Optimized edge processing and split rendering architectures aims to minimize this latency, ensuring that the virtual environment responds quickly to user movements. This is crucial for maintaining immersion and preventing disorientation or motion sickness. The latest scientific papers on next-generation wireless communication systems propose using delay-aware schedulers, which differentiate between URLLC and non-URLLC traffic to further improve latency. These new types of schedulers employ concepts like burst limiting shaper mechanisms, which provide tailored quality of service guarantees and therefore ensure that latency-sensitive applications receive priority over others. Another concept under investigation is the polite paradigm, which is short for power optimization for low interference and throughput enhancement. This method emphasizes algorithmic implementation and performance assessment for generic delay requirements, providing benefits in terms of increased throughput and delay satisfaction with transmit power reduced compared to current baseline link adaptation schemes. But despite their advantages, these advanced scheduling mechanisms face challenges in implementation. For instance, the complexity of real-time adaptation and the need for sophisticated computational resources must be considered and addressed when applying machine learning-based algorithms with these concepts. The question remains of where these requirements in terms of data rate and latency originate from. I can assure you they are not coming from nowhere. In fact, based on analysis from technologists, industry experts, and various industry forums, here are two examples. On the left, you will see an overview provided by the Virtual Reality Industry Forum, summarizing the requirements based on different levels of virtual reality and how data rate and latency requirements enhance based on video resolution, field of view, pixels per degree, frame rate, and several other parameters. Entry-level VR, for example, with 8K resolution and a 90-degree field of view, already requires a data rate of 100 megabits per second. Now think about a cellular network and mobility and cell edge conditions where it is quite challenging to provide such data rates given current spectrum allocations. The second example on the right is from Ericsson, where a team of researchers studied and analyzed the network behavior for a cloud-enabled AR service, which behaves similarly to cloud gaming applications, and uses SLAM, short for simultaneous localization and mapping and object detection, OD. The table summarizes the latency contribution in device and edge processing. It is clear that SLAM, object detection, rendering, and video encoding decoding contribute the most to latency, thus reducing the available budget for network-related latency. The shown latency varies between components since it is dependent on object complexity and hardware capabilities to handle that complexity. So the question is, how can we provide these data rates to fully enable the metaverse? And how can we deal with the complexity of latency based on the various components that contribute to it, often in a varying fashion, depending on the use case and the complexity? The evolution of wireless communication systems has been driven by the continuous optimization of key parameters to achieve higher data rates. This optimization is rooted in Claude Shannon's theorem, which defines channel capacity based on factors like the number of antennas, or MIMO modes, available bandwidth, and signal to interference to noise ratio, SINR. Initially, the focus was on channel coding practices, followed by advancements in modulation, coding schemes, and link adaptation techniques. The introduction of multiple antenna transmission and the expansion of available bandwidth have been significant milestones. Bandwidth, intrinsically linked to frequency range, has evolved with each generation of wireless technology. With 5G, millimeter wave frequencies were introduced, and for 6G, the industry is exploring frequency range 3, spanning 7.125 to 24.25 gigahertz, and sub-terahertz frequencies between 100 and 300 gigahertz. FR3, in particular, is relevant to our analysis of data rate requirements for XR-based services and applications. For instance, Nokia's analysis for a 16K resolution video at a 60 Hz frame rate with 12 bits per pixel indicates a need for a data rate of 450 megabits per second, translating to a spectral efficiency of 0.45 bits per second per hertz. In the quest for higher data rates, 5G networks utilize the 3.5 gigahertz spectrum with 100 megahertz channels using 256 QAM and 4x4 MIMO to theoretically achieve speeds up to 2 gigabits per second. However, consistently reaching these speeds, particularly at cell edges, is challenging due to current limitations. A key solution is the exploration of wider bandwidths, especially in the lower part of the FR3 spectrum, between 7 and 16 gigahertz. This spectrum offers the potential for channel bandwidths up to 5 times greater than today's FR1 range, with initial simulations by industry leaders suggesting a capacity increase of up to 10-fold. The FCC's investigation into the 12.7 to 13.25 gigahertz range, offering 550 megahertz of bandwidth, is a significant step in this direction. However, the industry must study interference and coexistence scenarios and address identified issues to protect the existing incumbents. Only this can ultimately urge global regulators to reconsider current spectrum access rules and enable equitable sharing of the spectrum among different services. The exploration of terahertz frequencies, especially from 100 to 330 gigahertz, where bandwidths exceed 10 gigahertz, opens new frontiers for the Metaverse and XR applications. Initially, these frequencies were considered for front hauling, such as connecting millimeter wave base stations to the core network via sub-terahertz wireless links. However, an intriguing potential XR use case for these frequencies lies in enhancing an application's user interaction and real-world spatial mapping capabilities. Specifically, higher available bandwidth at the sub-terahertz frequencies could enable very high-resolution gesture recognition and 3D scanning capabilities. With 10 to 20 gigahertz of bandwidth, we could theoretically achieve millimeter-level precision. This research avenue promises to accelerate advances in XR gesture interaction, making applications more intuitive and immersive, significantly enhancing the user experience in virtual environments. High spatial precision will also drive the creation of advanced mixed reality experiences, which seamlessly 3D align and blend virtual content with objects and spaces in the physical world. Now, I would like to conclude with 4 key takeaways on the role of 5G and 6G in enabling the Metaverse and XR. First, the evolution of 5G today and 6G in the future will unlock the Metaverse's potential by enabling higher data rates, lower latencies, smaller device form factors, new edge compute capabilities, and delay-aware scheduling. Next, the Metaverse's data rate and latency requirements are driven by the need for delivering 8K to 16K resolution content with no perceptible latency, while distributing processing for rendering, tracking, object detection, and other tasks. To consistently deliver the high data rates required by Metaverse applications, frequency range FR3 spanning 7.125 GHz to 24.25 GHz and sub-terahertz frequencies between 100 and 300 GHz are under consideration for 6G and offer the potential for much greater channel bandwidth than today's 5G FR1 range. And finally, terahertz frequencies can enable high-fidelity gesture recognition and 3D spatial sensing capabilities. That concludes our video on the role of 5G and 6G in the Metaverse and extended reality. Thank you for joining, and stay tuned.